Check this out. N squared divides 2 to the power of n plus 1. It looks so simple, so innocent. But it's actually a soul-crushing nightmare in disguise, a classic Olympiad trap that has claimed many brave souls. I love a good challenge, though. Let's poke it with a stick and see if it bites. We'll start by plugging in some numbers. 1 squared divides 2 to the first power plus 1, so 1 divides 3. Easy points. We're off to a great start. 2? Absolute disaster. 4 doesn't divide 5. Sorry, number 2, you're not on the guest list. Wait, there's a reason for that. 2 to the n plus 1 is always odd. For n squared to divide an odd number, n itself must be odd. 3 works, though. 9 divides 9. Now we're cooking. Notice a pattern? Maybe it's just odd numbers? Or maybe powers of 3. Let's go big and try 9. 81 dividing 513? Sounds plausible if you don't think about it too hard. Big nope. 513 divided by 81 leaves a remainder of 27. My disappointment is immeasurable, and my day is ruined. So, 1 and 3 work, but then the party just stops. How do we prove there aren't any more solutions hiding in the shadows? We need a heavy hitter, a tool so sharp it slices through Olympiad problems like butter. Say hello to the smallest prime factor. Specifically, let p be the smallest prime factor of n. This little guy is the key to unlocking the whole mystery. Recall from our initial search that n must be odd. Since n is odd and greater than 1, it has a prime factorization. Let p be the smallest prime factor of n. If p divides n, then p divides n squared. Consequently, p must divide 2 to the n plus 1. Squaring both sides, we get 2 to the 2n is congruent to 1 modulo p. Let d be the multiplicative order of 2 modulo p. From 2 to the 2n is 1. D divides 2n. From Fermat's little theorem, d divides p minus 1. Thus, d divides the greatest common divisor of 2n and p minus 1. Since p is an odd prime, n and 2 are coprime. We can factor out the 2 from the GCD. Recall, p is the smallest prime factor of n. Any prime factor of p minus 1 must be smaller than p. Since there are no common factors, the GCD of n and p minus 1 is 1. Also, p is odd implies p minus 1 is even, so the GCD of 2 and p minus 1 is 2. If d divides 2, then d is either 1 or 2. D cannot be 1 because p divides 1 is impossible, so d must be 2. If d is 2, then 2 squared is congruent to 1 modulo p. This implies p divides 3. Since p is prime, p must be 3. We have determined that the smallest prime factor of n is 3. We know 3 is a factor of n. Let's express n as 3 to the power of k times m, where m is not divisible by 3. Since n squared divides 2 to the n plus 1, the number of factors of 3 in n squared must be less than or equal to that in 2 to the n plus 1. This implies 2 times the valuation of n is less than or equal to the valuation of 2 to the n plus 1. We can calculate the valuation on the right side using the lifting the exponent lemma. Applying LTE with p equals 3, x equals 2, and y equals 1. Combining our two inequalities, we have 2 times the valuation of n is less than or equal to 1 plus the valuation of n. Solving for v3 of n gives v3 of n is less than or equal to 1. Since 3 is a factor, the valuation must be at least 1. Therefore, n contains exactly one factor of 3. We have found that n must contain exactly one factor of 3. Let's see if there are any other prime factors. We write n as 3 times m, where m is not divisible by 3. If m is greater than 1, let q be the smallest prime factor of m. Again, let d be the order of 2 modulo q. As before, d must divide the GCD of 2n and q minus 1. Since q is the smallest prime factor of m and q minus 1 are coprime. Therefore, d must divide 6. D cannot be 1 or 2, as that would imply q divides 3, which contradicts q is greater than 3. This leaves d equals 3 or 6, which implies q divides 63. Since q is greater than 3, q must be 7. However, if q is 7, then 2 to the n plus 1 is 0 modulo 7. Since n is a multiple of 3, 2 to the n is 8 to the m. 8 is congruent to 1 modulo 7. This leads to 2 congruent to 0, a contradiction. Thus, m cannot have any prime factors. Therefore, m must be 1, so n equals 3. Including our earlier finding, the only solutions are n equals 1 and 3. By systematically analyzing prime factors, we have completely solved the problem.